So, energy possessed by an object because of its state or position is called potential energy. Okay, in developing a thermocouple, a device that converts heat into electric energy, who showed heat was a transfer of energy? Seebeck. Okay, number 3, the total amount of kinetic and potential energy possessed by an object is its mechanical energy. Okay, who showed that chemical energy could be converted into electrical energy? Volta. What did he make? First battery. If you wrote volta pile, that's fine too. Okay, number 5, when two atoms are forced together to make a new atom, energy is released. This is nuclear fusion. Okay, and Count Rumford discovered while making cannons that mechanical energy can be converted into heat. Okay, it's out of 8. So give him a mark out of 8. We'll let him see it and then put him in a neat pile on this desk. So for number 2 here, it says state the first law of thermodynamics. The first law of thermodynamics says that energy cannot be created, it cannot be destroyed. Okay? You can change the energy of a system by doing work or adding heat. Okay? Those are the only 2 ways you can change the energy of a system. Okay, what is the distinction between work and heat? The thing they had in common was that they are both transfers of energy. What's different is heat is a transfer of thermal energy. Work is a transfer not just of kinetic, also of potential. It's a transfer of mechanical energy. Remember, it can be both. Okay, all right. Number 4, identify whether each of the following is best explained by the first law, which is energy can't be created or destroyed, okay, or the second law, energy flows from high energy to low energy or away, okay, of thermodynamics. A bouncing ball eventually comes to rest on the floor. Second, the only reason it comes to rest is because energy is flowing away from it. Okay, if it said energy couldn't be created or destroyed, that doesn't really explain that, because that kind of looks like energy is destroyed unless we account for the fact that sound and heat and things like that are produced by the ball bouncing. Okay, this is being explained because energy is being lost to the surroundings. Okay, B, a metal spoon eventually becomes hot when placed in a pot of boiling water. Also second law, okay, because energy is flowing into the spoon from the hot water. Energy flows from hot to cold. C, energy can't be created or destroyed. First law, yeah, okay. Number 7, state the second law of thermodynamics, which really should have come before this question in my mind. But okay, the second law is that energy flows from a high energy object to a low energy object. Okay, they specifically stated as heat moves that way. Okay, but heat isn't a form of energy. Thermal energy goes that way. Okay, I think it's easier to say high energy to low energy. Number 9, water is observed to condense on the outside of a cold glass. Which way is heat flowing? Right. The energy is flowing from the water vapor in the air to the glass. Okay, that's why the water vapor is condensing on the glass. The glass is colder. Okay, so when the water vapor touches it, it loses energy to the glass and changes state from gas back to liquid. Okay, the fact that it condenses on the outside is the evidence that it is losing energy to the water. Okay, does everyone follow me there? Okay, number 10, which law of thermodynamics best describes the following statements? You can't get something for nothing. First law, yeah. If you got something for nothing, you're creating energy. Can't do that. Okay. You can't even get close to getting something for nothing. Yeah, still first. Yeah. Okay. We can't create energy out of nowhere. Okay. Yeah, B is terribly worded. Okay, it should say you can't even get close to getting something for nothing. Okay, is at least the way I interpret that one to be. Okay, the reason you can't get something for nothing is we said perpetual motion machines don't work. It's actually kind of a combination of both. Okay, you can't create energy, so you can't get something for nothing, and you can't. Energy is always flowing away, so you can't have something that's doing it, that's giving you energy for free, essentially. Okay, and a rock will never suddenly jump into the air. Also, they're all first law. Okay, they're all first law. A rock will never suddenly jump into the air, thankfully. Okay, because well, that would mean that it just suddenly had energy it didn't have before. All right, questions on any of those? Okay. Now, again, this isn't in your notes package, but I basically never ask anything about this. It's just looking at the development of certain types of technology based on our lack of understanding of thermodynamics and then our understanding of thermodynamics. Okay, in terms of machines and thermodynamics, this is one of the cases where we didn't understand something but harnessed it anyway. Okay, we made a lot of machines even though we didn't really have an understanding of why they worked. Okay, we were just able to do it, right? Which kind of begs that question that's always asked by science: just because you can do something doesn't mean you should do something. Okay, there's kind of always that question in there. I mean, granted, this stuff is pretty harmless, but it's certainly a few cases here where that seems like it'll work. Doesn't really matter why, but it does, right? Okay, so one of the first types of machines that people wanted to invent was something that could move water from low elevations to high elevations. Okay, sometimes that would have been for like irrigation. Okay, sometimes it would have been to clear water from mines because water tends to collect in the bottom of mines and that makes it hard to mine. It's kind of dangerous. Okay, so we had these like the Archimedes screw, which is like a big auger. Okay, if you've ever gone ice fishing and augered a hole or you built a fence and had to make post holes, okay, you've used an auger before. Essentially, it's just an inclined plane. Okay, in the words of Sheldon Cooper, if you ever get yourself into real trouble, you become an inclined plane wrapped around an axis. You're screwed, because that's what a screw is. Okay, a screw is an inclined plane, a ramp, wrapped around an axis. It is funny. You'll get it eventually. Okay, that's essentially what this is. Okay, it's basically just a ramp, and if you spin it fast enough, though, you can kind of get the water to go up the ramp. Now, the limiting factor on this was how fast you could spin it, because how fast you could spin it determined whether you could move water all the way up or not. If you spun it kind of slow, the water just kind of hung out at the bottom. The faster you spun it, the further up it would go. But it did have kind of an upper length of only a couple of feet. Okay, because beyond that, you just couldn't make it go fast enough to draw the water up and create this kind of the siphon that would make it work. Okay. We also have the Persian wheel, okay, which essentially would bring water in these cups as you spun it, and it would dump the water onto this thing, which it would have then enough velocity to run somewhere else, and it was kind of a weak pump, but it worked. Okay. And then higher technology would be the reciprocating pump. Okay, and the reciprocating pump has a piston, okay, and two sets of valves. So it can actually pump in both directions. Whether the piston is moving in or the piston is moving out, water is moving either way. Okay, as you turn this wheel here, you are going to be lifting this valve, okay, and pushing this valve and lifting this valve as well. Okay, that's going to draw water in to the pumping area. Okay, and then once the piston changes direction and starts going this way, okay, it's going to close the bottom valve and push water out through the top. Okay, everybody follow? So when you're drawing water in, sorry, I said this one moved up when this one did. They actually move opposite each other. So when you're drawing water in and the piston is moving this way, this one's drawn up, this one's drawn closed, and that creates a suction that pulls water in, okay? And then when the piston is moving back this way, it forces this valve down and this valve up, and water moves past the valve, and you've got a pump going, okay? That's essentially how all of our modern pumps essentially work, okay? All right. So technology doesn't appear out of nowhere, okay? It's usually the result of a lot of trial and error and design and research and things like that. And then, of course, improving on people's designs, okay? We're looking at the development here now of engine technology, okay? Essentially combustion engine technology. The first combustion engine was an internal combustion engine, not like what we use today. It was the gunpowder engine, which, as its name would imply, did not work very well. Okay. Essentially, what they did is they just had a sealed container with a piston in it. And they would have gunpowder in there, and they would detonate the gunpowder in the same way they would detonate it with a cannon. They had a little wick, okay, that came out, and they would light the wick, and then boom, and it would blow up. And the explosion of expanding gases would push the piston up in the air. And that's it. Okay, it couldn't run more than one time, like a modern internal combustion engine cycles, right? It reciprocates and keeps going. The gunpowder engine was good for one shot and one shot only, and then it had to be completely reset, often rebuilt, okay, because the explosion of gunpowder is, well, destructive. And if you didn't build the cylinder to hold that those expanding gases very well, it would rupture and people would get hurt. Okay, so it wasn't a great thing, but it did show that expanding gases could be used to do work. Okay, and that was an important kind of first step in the development of a piston-operated internal combustion engine. Okay, we talked about the heat engine yesterday. Okay, sorry, the drawbacks, obviously, of the gunpowder engine was not developed. It was just kind of a design. Okay, because of the obvious hazards of explosions and because there was no powerful internal mechanism to pull the piston back down. Okay, so that created a problem. Okay. We talked about the heat engine, okay, which was by Denis Papin, okay, and he did not pursue the development of his engine because he had difficulty making a large drum in which the water was to be heated, okay. The Savory engine, okay, was one of the first kind of steam engines, and it was used to pump water, okay. So basically you had this big boiler, okay, so it was an external combustion engine. Steam engines are external combustion. Okay, so the fire is here. It heats the water. Okay, the water turns into steam. The steam goes into here, which could then push down the pistons. Okay, or cause the pistons to move because obviously gaseous water takes up more space. Okay, so the pump could lift water to a height of only 6 meters. So it wasn't much of an improvement over ones that were animals connected to wheels. Okay, to lift it higher distances, the steam would have to be under higher pressure, and at that time they couldn't machine the containers well enough to maintain a seal, right? Because you couldn't really put rubber in there. Their technology for making rubber wasn't as good. Rubber would melt, and it wouldn't maintain the seal. It was hard to get metal seams to seal properly. Steam would leak out and scald people. Okay, so it wasn't really good for moving things much of a distance. Okay, the boiler could not produce that amount of pressure without exploding. Okay, you got gases under pressure, you're going to possibly have that happening. Okay, the Newcomen engine, okay, was another one, and it was using obviously steam as the driving force. Okay, it only produced steam, or sorry, a boiler produced steam that forced a piston up in the cylinder, and then cold water was sprayed on the outside of the cylinder to cool it. So how fast was this engine? Very slow. Okay, it was not very practical. You heated it up, you got the steam in there, the steam would get going, okay, and it would push the piston up, and then you had to spray it with water to cool it down and make the piston come back down. All right, so it was heat it up, cool it off, heat it up, cool it off, and probably like put out the fire each time you sprayed the thing with water. So while it worked, it wasn't very practical, and it wasn't very fast. Okay. Right. It was easy to build because it wasn't very good, okay, and it was easy to maintain, and it could pump water to higher distances, but the cycle of heating and cooling was really, really slow. Okay, so that wasn't advantageous at all. Okay, Watt, okay, he came along and he developed essentially the first effective steam engine, reciprocating steam engine. Okay, he was actually in charge of repairing all the Newcomen engines when they would rupture. Okay, so he saw what all the flaws were and then went, sweet, I've figured out what this guy did wrong. Now I'm going to go to the patent office with my better design and get rich. And he did. And his design was so good that he actually has the units for power named after him. Okay, so always a good sign that you did something right. Okay, so he repaired Newcomen engines, and he was, of course, shocked by their poor performance. Okay, so he made this steam engine, okay, that reduced the amount of heat required to operate it, okay, making it more efficient. And obviously, his steam engine dominated for a very long time. Okay, the drawbacks were that they were easy, even though they were easy to build, they were huge. Okay, so it wasn't something you could use in a vehicle. Right? You couldn't use it to power a train or a car or anything like that. Okay, it was just too big. It was fine for making pumps in areas or industrial areas where you had lots of room, but it just was really, really big. Okay, they were hot, they were dirty, they burned coal, okay, all of that kind of stuff. So yeah, they weren't great in that regard. All right, the internal combustion engine. Okay, so going away from steam. Steam is fine, but you have to burn a lot of coal to get it. That makes it kind of inefficient, right? So finding something that has the combustion chamber inside, using the expanding gases inside, has the ability to reciprocate more quickly. Okay, so that was the idea behind this. So Robert Steele was looking for a different source of fuel, okay, and he ended up using this coal gas that came essentially from, well, the mining of coal was kind of this associated gas, okay, and like I said, it used coal gas that was ignited by an electrical spark, which is, of course, how the internal combustion engine now works. Okay, if you know anything about engines, they have things called spark plugs in them. Okay, and the spark plug just has a very narrow gap, and electricity arcs across the gap. That arc ignites the fuel, okay, inside your engine. Still to this day, that's what we use to ignite fuel. All right, put that down. Okay, so the drawbacks with the coal-fired engine or the coal gas engine. Coal gas is not a very high enthalpy fuel. It doesn't get really, really hot, and it's dirty, so that the engine would foul a lot. If you have any engines that are two-cycle engines, like if you have a chainsaw or a weed whacker, some like small motorcycles where you have to mix oil and fuel together in one thing, okay, that's kind of like that fuel mixture is kind of like what this mixture was, and it was full of oily deposits that would get on the internal parts of the engine and cause it to foul and not work very well. Okay. All right, then we have a little bit later on, okay, we have Otto and Eugen Lagen. Okay, they improved on the efficiency by using compressed coal gas. Okay, and that's like a huge step. In our internal combustion engines, the pistons, as you can see in this diagram, move up and down. The compression of the air-fuel mixture is what makes the internal combustion engine work, right? So you move the piston up and you compress this gas and air together, which makes the ignition more intense. Okay, so there's a couple of phases here. Okay, there's the intake phase. That's the first phase of the internal combustion engine. So the piston moves down. Okay, while that is going on, the intake valve or valves are open, and the air-fuel mixture is pulled in by the vacuum created by the piston moving down. Because as the piston moves down, it creates a low-pressure area. Okay, in the same way, if you've ever used one of those water guns that just has the squeeze kind of thing on it, right, where you push it in. Okay, when you're drawing water in, you do this, right? You pull it up. It's the same idea. This is the intake phase where the piston is moving down. It creates a vacuum that sucks the air-fuel mixture in. Right. Once the piston has reached the bottom of the cycle, it returns to the top. That's called the compression phase. Okay, so during that time, the piston is moving up and it is putting that air-fuel mixture under pressure. Okay, when it reaches the top and it's compressed its maximum amount, that's when the spark plug fires. Okay, it ignites that air-fuel mixture, and the expanding gases push the piston back down in what's called the power stroke or expansion phase, okay, of the movement. Okay, so that's where the engine actually does work. Okay, then there's another phase where the exhaust gases that are produced have to be expelled from the cylinder. Okay, this whole thing here is the cylinder. Okay, the piston moves up and down. This is the piston. Okay, moves up and down in the cylinder. Okay, you have a crankshaft. Okay, and then this down here is connected to essentially the drivetrain. Okay, so in this phase, the exhaust valve opens up and the exhaust gases are expelled. Okay, this is why typically the more pistons you have, the better, or the more power you generate, because not every piston is firing at the same time. In fact, usually only one is firing at the same time. Okay. Anyone ever done any work on cars or engines? Okay. There's a lot that goes into making this work properly. Okay. There's things like timing. You can actually adjust when the spark plug fires. If the timing is off, it fires early or late. Okay. If it fires early or late, the gases aren't properly compressed and you don't generate as much power. You want it to fire when the gases are at their maximum compression. Okay. If your car isn't timed right, you can actually hear it. If you're listening carefully for it, it makes kind of a ticking or a pinging sound. Okay, if it's firing early or late, because the gases don't create that massive expansion, and the piston actually moves down poorly and makes an odd sound, a pinging sound, okay, that you can actually hear. All right, so that's kind of how the internal combustion, basic internal combustion engine works. The ones that we use now are more complex than this. This is one that would only have 2 valves. Okay, most cars now, I don't even think you can get a car that runs on just 2 valves anymore. Most cars have 4 valves, 2 intake and 2 exhaust. Okay, that makes them more efficient. They breathe better. Okay, they are more fuel. They're more fuel efficient as a result. Okay, but a lot of this stuff now is computer controlled. Okay? There's sensors all over your car that detect the concentration of oxygen in the exhaust gases, the concentration of oxygen in the intake gases. They adjust the timing automatically. Okay? The computer in your car makes all of those decisions in a split second all the time. Okay, I'm never going to ask about that, but people are often curious if they don't know much about cars how that whole idea works. Okay, don't get the idea you could service your car now. Okay. They hook it up to a computer and do all that. All right, so almost every engine in the early 1900s, okay, was an auto engine, okay, and it could produce the same amount of power as a horse. 1 horsepower. Okay, that's where the units horsepower came from. Okay, when they first developed engines and we were building tractors and things like that, farmers came into the tractor dealership and said, okay, I want to buy a tractor. How many horses will it replace? Okay, that's what they needed to know. I pull my plow with horses. I need 5 horses to pull my plow. I need something that replaces that. Oh, well, that's perfect. We have this 8 horsepower tractor. And the farmer would go, sweet, I was using 5 horses. Think how much faster I'll do this now. I have an 8 horsepower tractor. Okay, so that was kind of where that idea came from. We don't use horsepower in the metric system. Okay, we use watts as the units for power, but most of us don't know what a watt means. Okay, like when I went car shopping, I noticed that they actually had watts on some of the cars as a power rating. I'm like, it's a 5 kilowatt engine. I have no idea whether that's good or bad because it's not in horsepower and I don't know. Okay, kilowatts, 1,000 watts, it's 5,000 watts. Is that good? I don't know. Okay, hybrid cars will often have the power rating in watts, and it's just, yeah. Just tell me how many horses it is. I got to know that. Okay, that's more meaningful. Okay. Yeah, we don't need to worry about the future technologies one, and we're not going to do those. So, okay, just so you know, that's kind of how those work. Okay, go to lesson 6, scalars and vectors. Okay. So now we're getting to the more measurement-oriented, math-oriented part of the unit, okay? And from here on out for a while, it's going to be a lot of okay, here's a formula, here's some problems that have to do with that formula. We got to practice using it, manipulating it, okay? Things like that. We're going to look at graphing as well here in the coming weeks, and do some labs on movement and energy and things like that, okay? So scalars and vectors, okay? If something is or has a vector, what does it have? It has a measurement, but that measurement also has what attached to it? Okay, let's imagine this situation. You are from Nicaragua, and you are here in Okotoks. You have never been to Canada, and you have never seen a map of Canada. And I tell you, oh yeah, the Calgary Stampede is going on, and it's in Calgary, and it's like 40 minutes from here. What's that going to mean to you? Absolutely nothing. You have no idea where Calgary is. And I've told you it's 40 minutes from here. How helpful is that? Not very helpful. Okay. Cody, if I ask you how far it is to Edmonton, what would you tell me? A few hours. How many of you are thinking the same thing? 3 hours? That's our problem. Okay. We as North Americans have this totally messed up way of telling people how far away places are. We tell them how long it takes to get there, and that is totally wrong. Okay, I'm sorry, I hung out to dry there, Cody, but okay, it wouldn't have mattered who I asked. I get that question, that answer like 95% of the time, because that's how we think. Okay, we've been trained to think that way because we have this vast interconnected system of roads that we can follow to go anywhere. Okay, and they have speed limits, so we know about how long it takes to get places. Except it doesn't always take that long. Sometimes it takes longer. much longer. Okay, I've had times where driving home from Edmonton took like 8.5 hours. Okay, because how long it takes me is dependent on what? Traffic. In other words, how fast can I go? Because the distance from here to Edmonton never changes. Edmonton has not moved. Okay, it is still where it always was, and so is Okotoks. Granted, the cities themselves have gotten bigger, but they are still where they always were, and they're always the same distance apart. Okay, that part doesn't change. So when I tell somebody, oh yeah, it's 3 hours to Edmonton, I might have lied. It's 3 hours if I go the speed limit, and there's nothing between here and Edmonton that causes me to slow down. Okay, but the reality of it is there's almost always something that causes you to slow down. Okay, maybe you have to go to the bathroom at Gasoline Alley in Red Deer, or maybe there's construction, or it's a terrible storm right around Olds where there's always one. Okay, and you end up getting slowed down, and it ends up taking longer than that. Okay, so what we have to first overcome in physics is this way we think about distance. Okay, distance is how far in meters or kilometers or centimeters, okay, something is from something else. Point A is from point B. Okay, the time it takes to get there is measured in seconds or hours or whatever. Okay, but we gotta stop thinking of distance as time because they're two different things. Okay, now back to this example of the person from Nicaragua. I tell him it's 40 minutes to the Calgary Stampede. What's he gonna do with that? He's probably going to ask me which way, because I didn't tell him that. I assumed that he knew where Calgary was. That's not always a safe assumption. Okay, so he would have 360 choices for which direction to go. Agreed? Okay, I mean there's 360 degrees in a circle, right? Now, granted, I mean we're pretty close to Calgary, and Calgary's pretty big. Maybe 35 of those 360 might end up in Calgary somewhere. Okay, but they certainly wouldn't end up at the Stampede. Okay, maybe 1 degree out of 360 would actually get him there. Right? So if I give him a vector description of where the Calgary Stampede is, okay, I would tell him something more like it's 35 kilometers from here and it's 35 kilometers north. Okay? Now I've given him a vector description. I've told him how far it is and what way to go. All right? That's often more useful than just saying it's 40 kilometers from here. Okay, or 35 kilometers from here. Which is more accurate, 35 kilometers north or 35 kilometers? They're the same. Accuracy has to do with your measurement, not the amount of information you give. Okay, I said it was 35 kilometers in both cases. Okay, I said it's 35 kilometers. That means it's 35 kilometers plus or minus 1 kilometer. This is the last digit I measured. Everybody follow there? Okay, so I gave him a measurement that was accurate to plus or minus. Okay, if I told him it's 35.1 kilometers, now I'm accurate to plus or minus 0.1 kilometers or 100 meters. Okay, that is more accurate than this. Okay, but saying 35 kilometers and 35 kilometers north is the same accuracy. One has more information, but they're measured to the same accuracy. Okay, so never get confused with accuracy versus amount of information. Okay. All right, so there's many ways of measuring how far apart or how fast objects are going. Okay, differentiate between distance, displacement, speed, and velocity. Okay, how many people think speed and velocity are the same thing? You don't want to admit it, but most of us do. Okay, most of us think they are the same thing. They both measure how fast something is going. But one of them is a scalar quantity, one of them is a vector quantity. Okay, if you go out on the Deerfoot and you go 140, you're probably going to get what? What kind of a ticket? Speeding ticket. If you get a speeding ticket, does the officer write on there which way you were going? Only if you were going the wrong way. That's a separate ticket. Okay, if you're going 140 southbound on northbound Deerfoot, you're probably going to get additional tickets for that. Okay, but they don't give you a velocitying ticket because it doesn't really matter which way you were going. All that matters is the magnitude of your speed, how fast. Okay, speed does not imply direction. Okay, it is a scalar quantity. Velocity does give direction. So when I give the velocity of something, I have to give a direction as well. How fast were you going? Officer, my velocity was 140 kilometers north. He's probably going to think you're a smart aleck if you say that, so I would advise against it. Okay, just tell him how fast you were going. He only wants to know your speed. He does not care about your velocity. Okay. Distance and displacement work the same way. The distance between two objects is a scalar quantity. We only say how far it is. Okay? We don't say what direction. If we're giving the displacement, then we do give the direction. It's a vector quantity. All right, so I'll go into a little more detail on the difference between those things here in a sec. All right, so if you've ever gone hiking off trail or done any orienteering, okay, you well know that how we describe travel in everyday life is effective only for getting you hopelessly lost in a roadless or trackless environment. Okay, because I mean, you look at our road signs, right? Like you get on the highway and it says Edmonton, 290 kilometers. What is it assuming? Right, that you're going to stay on the road. Is that road straight north? No, it's got turns in it. Okay, and that's accounted for in the distance traveled. Okay, so if I'm looking at the that's not bad. Okay, all right, so we're going to go. Okay, from Calgary to Edmonton. Highway 2 does not go straight from Okotoks to Edmonton or Calgary to Edmonton, right? It's got the little turns in it and whatever, and okay, it does something like that. I mean, it's mostly straight, but it's got some turns in it. So the distance from here to there is every little piece of this path. Okay, it's not this line. Okay, that line that I just drew, the straight one, is the displacement. The straight line distance and direction that it is from point A to point B. Okay, this line, squiggly line, is the path I actually have to follow. That would be my distance traveled without direction. I can't really give a direction because I went a whole bunch of different directions in traveling from A to B. Okay, does everyone follow me there? That's why our signs on the roads tell the distance and not the displacement. Okay, now it's a totally different thing if you are a pilot, because then you can follow that line and you do need to know what direction to go. Okay, and you have to correct for things like wind speed, okay, that might try to push you off course. Okay, all that stuff is corrected for as a pilot. As a pilot, you deal completely in vectors. Okay, and dealing with, okay, I got to fly, to this point, and then I got to go this way, but no, I can actually fly in a straight line, so I'm going to do this, and I'm going to go this direction, and I have to keep on this heading. Okay, everybody follow there? Okay, so if you're thinking of becoming a pilot, okay, your life is going to be all about vectors, okay, and displacement and velocity and other vector measurements. Okay, so if we're looking at this map here, okay, this is a hike that my father and I did. It's 218 kilometers, okay, and it's through really harsh wilderness. Okay, this is the North Boundary Trail in Jasper. Okay, so it's along the north boundary of Jasper National Park. The signs or the signage on this hike, in our mind, was crap. Okay, because every time we came up on one, it's like, okay, it's the one that was in particular that was here at Seldom Inn Campground. Okay, said that it was like 28 kilometers to Snake Indian Falls Campground. We're like, okay, that's telling me this distance along the path. Correct? Yes. Okay. Signs always tell you the distance, assuming you're going to follow the path. Well, the problem is the path deteriorated to the point where the path was gone, and we ended up having to kind of freelance a path other directions, which really was bad because there's all manner of disaster off the path. Okay. And so it ended up being a lot further than the sign had said. Okay, had there actually been a set path, then that would have worked. Okay, it didn't tell us this. Why would a sign not tell me that? Not without a helicopter. Yeah, I'm not going to go that way. not on foot. Okay, I mean, look, I got how many rivers I got to cross. This is a glacier here, so that's not so good. You're not supposed to walk across those. They're full of like crevasses and stuff. Okay, yeah, it would have been impossible to do that, and it would have been far more rugged because it would have been up and down and all kinds of rotten terrain. Whereas paths tend to follow river valleys and flat areas and things like that. They tend to be the smartest way, if not the shortest way, to go. Okay. All right, so we have to understand that in some cases, a scalar description, distance in this case, is better. Okay? It's way better on a sign to tell me the distance along the path than it is to tell me the displacement from 1 to 2. Because I'm not going to go that way. Right? People get this idea that, oh, well, scalar quantities are bad because they don't, they don't tell you direction and things like that. No, there's lots of times where scalar quantities are appropriate. Okay? And there's times where vector quantities are appropriate. Okay, everybody good with that? Okay. So we got to remember when we're communicating things like distance that we should communicate what we are meaning to communicate. Okay, I've been burned on that a whole bunch of times in backpacking trips. Okay, Buddy and I were doing the rock wall in Kootenay National Park, and we had this one really long day, 2 passes, and it was like 26 kilometers, and it was about 5 o'clock, and we weren't at the campground yet. And we passed this guy who, when we finally got to the campground, really occurred to us that we really asked the wrong guy. He passed us, and he was wearing like military fatigues and was carrying like a big pack, but he was motoring, and he was motoring uphill. We were walking downhill at this point because we'd gone over the pass. And like I said, it was 5 o'clock in the afternoon. And we asked him, hey, you must have come from Tumbling Falls Campground. He's like, oh yeah, it's like 20 minutes. 20 minutes down the path. I'm like, sweet, 20 minutes, we've been walking all day, or we're out of water, we got to filter some water and to have something to drink and get going. Yeah, 50 minutes later, we were at the campground, and we were cursing this guy, okay? Because he had told us it was only 20 minutes. It took him 20 minutes jetting uphill, took us 50 minutes to walk downhill to this place. Why? Because he's probably a Navy SEAL and was doing this as an exercise jog, okay? Whereas we were, out, enjoying the scenery. Well, we'd stopped enjoying the scenery and we're just suffering at that point. But, okay, it took us a lot longer because what was different? Our speeds were different, okay? He was way faster than we were, okay? And he told us how long it took him to get from A to B. That's why you should never tell someone how long it took to do something, only how far they are apart, because their speed is likely to be different than yours. Okay, everybody with me there? All right. Okay, so when we say Calgary is 40 kilometers away, we make no reference to which direction Calgary is. We just get on the road and we drive there. Okay, in this case, we have made a scalar description of where Calgary is. In other words, we have given the distance to Calgary, assuming a person is going to follow the road, okay, to Calgary. Everybody with me there? Okay, it's not a straight line. There's all kinds of bends in Deerfoot Trail, okay, that you would have to take in order to do that. Okay, another way, and I shouldn't say more accurate. In fact, I think in your notes package I took that off, right? Does it say more accurate in yours? Should be right after.
I'm not sure. It's somewhere in here.
This, a directional description would be, yeah, so I changed the notes for yours, yeah, because I'm saying here that this is more accurate. This is not more accurate. It's 40 kilometers. That's plus or minus 1 kilometer. That's what we talked about earlier, okay? That's why I changed yours, okay? A directional description or a vector description would be that Calgary's 40 kilometers away on a vector of 13 degrees east of north. But if you tell that to someone, they're going to look at you like you're crazy because that's not useful, okay? You're not going to walk in a straight line from Okotoks to Calgary. Okay, you'd have to cross rivers and people's private property and all that kind of stuff, barbed wire fences. Okay, it's not, and there's going to be buildings in the way. So unless you can, like walk through walls, okay, it's not going to work for you. Okay, it's just not practical in this way to give that description. Now, if they know you have a helicopter, then they might tell you that because you could fly to that point in a straight line and not worry about it. Okay, so the description is a vector description because it not only tells us where Calgary is, but also kind of how to get there, okay, by telling us in what direction to head. Vectors are not always measured in degrees. For you guys, we're not going to use compass directions because that brings trigonometry in, and you don't have to do that in Science 10, but it's the first thing we learned in Physics 20. Okay, we'll just use what we call one-dimensional vectors, positive and negative, up and down, left and right, okay, things like that, or north and south, or east and west, things that have a direct opposite, okay? So we're only going to be dealing with one-dimensional motion here. Okay, so distance versus displacement, okay? When we give the distance an object travels, okay, we've used a scalar quantity. It's 4 kilometers from my house to Walmart, okay? The displacement of the same trip may be 2.8 kilometers on a vector of 38 degrees north of west. Okay, again, that's the straight line distance from my house to Walmart. Okay, so distance and displacement are different measures of the same thing. They're both describing the same trip, but one is taking it from a how did you actually get there perspective versus one is what's the shortest route between those 2 points. Okay, so, oh, where'd my picture go? It's not on there. I'll have to redraw it. Okay. So let's say that, so where was my direction so it matches up here? North of west. Okay. So let's say that Wally World is over here. Okay, and my house is over here. I can't draw. I admit that. Okay, so if I leave my house, I follow the road and it's kind of curved and you can do whatever, but it's not a straight line. I eventually get to Walmart, eventually, okay? So that distance, if I walked it, is 4 kilometers. But I have displaced myself in a straight line a much shorter distance. Agreed? Okay. So the black line represents my displacement. And I've said that that was 2.8 kilometers on a vector of 13 degrees north of west. Okay, so I've given a vector description of how far it is from my house to Walmart. Okay, but that has to be a straight line. The scalar description is the measurement of this. How would you measure this curved line? Yeah, on a map, that's what you do. If you've got a curved path, you take a string or a shoelace or a headphone cord, okay, something like that, and you just make it take the shape of the path. And then once it takes the shape of the path, you mark each end with your fingers, straighten it, and measure it. Okay, and then you use the scale on the map to figure out how far that was. Okay, as opposed to measuring a straight line, which is quicker. Okay, and obviously the shortest route between 2 points is always the displacement, the straight line between them. Okay, everybody with me so far? Okay, is there a case where displacement and distance could be the same? Yeah, if you actually did what? If you actually went in a straight line, then distance and displacement could be the same. All right, so let's say that this trip, so this one here we said was 2.8 kilometers, okay, and this one is 4.0 kilometers. Let's say that that trip takes me a half an hour. Okay, so now I have my time. How fast did I walk? 8 kilometers an hour. Okay, how'd you figure that out? Times it by 2 for an hour, okay. Or, in his head, this is what he did. Okay, he took 4 kilometers and divided it by half an hour. When you divide by 0.5, it's the same as multiplying by 2. Okay, 4 divided by 0.5 gives you 8 kilometers per hour. Right? So I took distance, divided it by time, and I got speed. I know it's a V, okay, but V stands for speed. Why? Because so does velocity. But I put arrows over top of it to indicate that it is a vector quantity. It has direction. Okay? Because S stands for other things. So we can't use it for speed, right? It's the units for seconds, the abbreviation for seconds. So People get confused. People get confused about V too, but they just get used to it. Okay. So we got V equals d over t and V equals d over t. Now, if I want to calculate the velocity, I got to use the displacement divided by the time. Okay. Well, these are describing the same trip, so the time is the same. Okay. Yes, I displaced myself in a straight line. It didn't actually walk the straight line, so it still took me a half an hour to do this. So it's still a half an hour on the bottom. Okay, but now my displacement is 2.8 kilometers at 13 degrees north of west. Okay, it's all got to fit in there. So what's my velocity? 5.6. That's 2.8 times 2. Okay, so 5.6 kilometers per hour. What do I need to put on that? Okay, I divided kilometers per hour. What did I do with this? Stays there. 13 degrees north of west. Okay, remember, velocity is a vector quantity, and velocity and displacement have to be in the same direction. Okay, it would be impossible for me to travel at a speed of 5.6 kilometers south and end up over here. Agreed? Okay, so my velocity has this same vector, 13 degrees north of west. It would be, but remember, this is the same trip. I'm looking at the same trip from two different points of view. It's not two different trips. Okay, I walked this route, but from a vector perspective, all I did was this black line. This is how far I ended up in a straight line from my house by following the blue line. Yeah? Okay, everyone follow what I did there? Okay, now, I get to the doors of Walmart, and this is a real world situation because it happened to me, and I realized I'd forgotten my wallet. So, I turn around and walk exactly the same route home at exactly the same rate. Okay, what's my total distance traveled? 8 kilometers. My total distance traveled is 8 kilometers because I went 4 kilometers and then I went another 4 kilometers. Okay, I walked 8 kilometers in total. Okay, I heard someone jump the gun on the zero part here. Okay, what's my displacement for the whole trip? 0. Remember, displacement is how far and in what direction you are from where you started. My starting point and my ending point are the same place. Therefore, from a vector perspective, I have gone nowhere. Okay, and as a result, my displacement is 0. Okay, what's my average speed over the whole trip? Took me a half hour to walk there, a half hour to walk home. I went 8 kilometers. Still 8 kilometers per hour. Okay, guys, isn't that what I did? I went 4 kilometers in a half an hour, 4 kilometers in a half an hour. I went 8 kilometers in a whole hour. That's my speed, 8 kilometers per hour. What's my velocity? Velocity is displacement over time. What was my displacement? 0. So what's my velocity? 0. That's the kind of wonky thing, okay, about vector quantities. If you end up back where you started, everything is 0 from a vector perspective. Okay, it's kind of weird that way, but it's true. This is why the odometer on your car measures, no, the speedometer measures speed. The odometer measures distance. It measures how many kilometers are on your car. It measures distance traveled. If it didn't, every time you came home, it would read, no, it would read how far it is from the dealership you bought it at. Every time you take it to the dealership you bought it at, it'll read 0. Come on, guys. I set you up. No one ever gets that right. No one has yet to give me the right answer on that one. Everyone says, well, say 0. Really? So they dropped it via helicopter on your driveway. Okay, yes. Okay, if you had your car delivered via helicopter to your driveway, yes. Every time you come home, it'll say 0. And if you can afford a helicopter, you can probably afford to have a car that is delivered by helicopter. Okay. So does the difference between velocity and speed kind of make sense? Okay. And it's the same relationship with distance and displacement. Okay. They're looking at the same trip from two different points of view. All right, so that's what we've kind of gone over this writing here now. Okay. Well, I said 38. I said 13 on the diagram, but it doesn't really matter. Okay. Manipulation. We talked about the 3 rules of algebra back in the chemistry unit. Okay. The 2.5 rules. The 2.5 rules of algebra go as follows. You might want to write them down again in case you've forgotten them. Okay. The 2.5 rules of algebra are: to move a variable, do the opposite operation. That's rule number 1. That is true all of the time. If I move a variable, what else do I have to do? Do the same thing to the other side of the equation. That's rule number 2. What you do to one side of the equation, you do to the other. Okay. The last rule is the half rule, and it's a half rule because you don't always need it. Okay. In this equation, we're not going to need it. Okay. You really only need it if you have more than one type of operation. Like if you've got a formula that has multiplication and division and addition and subtraction in it, then you might need it. Okay. So rule 2.5: when moving variables, move what is not attached to your number first, or the variable you're looking for first. Move what's not attached first. Okay, so let's look at this from the perspective of the formula we're going to be using. V equals d divided by t. Speed equals distance over time, or velocity equals displacement over time. They're going to be manipulated in the same way. Let's say that I want to solve for d. What do I need to do? Austin? Right, multiply both sides by time. Essentially then, that's going to move t over to here. Okay, everybody with me there? Yes? Okay, so what I did, I hate it when that happens. Okay, essentially, what I did here is I said, all right, I need to move t. I'm dividing by t right now, so I'm going to do the opposite operation. I'm going to multiply both sides by t. Okay, and when I do that, I have t on the top and t on the bottom. T divided by t is 1. Okay, t divided by t is 1. Okay, so essentially, I've done this. I now have d over 1, which is just d. Okay, and over here I have t times v. Now I've solved for d. Everybody follow what we did there? Okay, that's probably the easiest manipulation of that. Whoa, that's big. That's too small. Got the Goldilocks effect going on here. Okay. Okay, now I want to solve for t. Yes. Okay. How many of you were wanting to leave t where it was? Okay. A lot of people want to leave t where it was by moving d. But if I move d by dividing both sides by d, what it gets left on top? 1. Okay. If I divide this by d, d divided by d is 1. I still have t on the bottom. I'm not solving for t. I'm solving for 1 over t, the inverse of t. That's not what I want. Okay. So I want to move t. You always want to solve for something when it's on the top of an equation. Okay, so the first thing I'm going to do is what I did in the last thing, which is multiply both sides by t. T is going to cancel on this side, and it's going to come over here. Now, t is on the top, but I want it by itself. I'm multiplying it by v, so what do I do to move v? divide by it. If I want to move something, I do the opposite. So I divide both sides by v. T equals d over v. Okay. Those are the only two manipulations of that formula you have to do. There's only three variables in it. Okay. Everybody follow what I did there? If you ever aren't sure if you've manipulated something correctly, you can do what's called a unit analysis, which is plug in the units for each measurement and see if you get the right units, right? So right now I'm solving for time, right? So let's say I had the distance in kilometers and the velocity in kilometers per hour. Okay, when I divide kilometers by kilometers per hour, okay, I get 1 over 1 over hours, which is the same as hours. Is that what my unit should be? Yes. Okay, and so I've correctly manipulated that, canceled off the right things, and I'm solving for t. Okay, ringing a bell for people. Okay, is this exactly the same as manipulating n equals little m over big M? It is, except you only had to do one manipulation of that formula. This one you got two. Okay, doesn't really change what you do. The rules of algebra still apply. Now, let's say we're manipulating something maybe a little bit more complex, like this one. Are the rules going to change? Nope. Rules are going to be the same. I want to solve for d. What should I move first? I should move VI. I want to move what's not attached first. Okay, that's the rule 2.5. This one is going to use rule 2.5. All right, so right now I'm adding VI squared to 2AD. So what should I do with it? I should subtract it. I want to do the opposite. All right, so what I'm going to have over here then now is VF squared minus VI squared equals 2AD. Okay, I want D by itself. What do I do? Divide by 2A, right? I'm multiplying all three of these together, right? So I want to divide off the things I don't want. Now I've got D by itself. Okay? If you can remember those 2.5 rules of algebra, you can manipulate any equation you want. Okay? You just have to let go of this fallacy that you've had in your mind that you can't do math and that algebra is hard. Okay? Because it's not true. Okay? If you can remember these 2.5 rules and follow them, you can manipulate any equation you want. And the more you do it, the better at it you get. Okay? Pretty soon you'll be manipulating this in your head without having to do this. All right? Let's look at a different one. Let's look at, I want to solve for VI. Minus 2AD. I want to move this over here, right? It's all together. I can move it all together if I want. Okay, so I'm going to go VF squared minus 2AD equals VI squared. I want VI. What do I have to do to both sides? Easier than that. Square root. Yeah, because if I divide this side by VI squared, that's not the same as square rooting it, right? Okay. Okay, well, the square root of VI squared is just VI, right? So now I've manipulated it. Okay, all I did was follow those rules of algebra. I moved what wasn't attached first by doing the opposite and doing it to both sides. Okay. What if I want to solve for A? Okay, first thing I should do is subtract VI because it's not attached to A. Right, so I'm going to have VF squared minus VI squared equals 2AD. Now what do I move? Okay, I divide by 2. Then what? Divide by D. I could have done that all in one step if I wanted to. Just divide by 2D. Okay. You can do it in 1 step or 2 steps, doesn't really matter. In the end, I still have the same thing. Okay. Is algebra making a tiny bit more sense? Smidgen. Okay, because here's the problem, guys. There's no triangle for that. Okay, yeah, you can draw a triangle for V equals D over T, but that's only going to hold you together for another couple of days, and then boom. Okay, everything after that, you will be destroyed in your little triangle world. Okay, will end. Okay, and you'll have to come up with a different way, which is the 2.5 rules of algebra. You can't go wrong with the 2.5 rules of algebra. Okay, I want you to write this one down. It isn't in your notes, but I want you to write it down. Okay, we're going to look at how do I calculate the average velocity of something if its trip has more than one part. Okay, which is a little bit tricky. Okay, so in a question like this, first thing we got to remember is that displacement is how far and in what direction you end up from where? From where you started. Okay, and we got to remember that velocity is displacement over time. Okay, this formula also means this. Average velocity is total displacement over total time. Okay, because what really messes with people when we first start talking about average velocity is that you've been taught that to calculate the average, you figure out all the little parts, add them together, and divide by the number of little parts. Except that that's how you calculate average on like a test for a class where everybody in the class represents an equal part of the total. In this trip, I cannot find the average velocity for each part, add them together, and get the average velocity because the two parts of the trip are not representative of equal halves of the trip. You guys follow me here? I went this way a lot longer than I went this way. So they are not equal parts. I can't add them together and divide by 2 because that says they represent equal parts of the trip, which isn't true. Okay, so what I have to do is picture this trip. I go 100 kilometers north. So here's my starting position. Okay, I go 100 kilometers north. And then I travel 62 kilometers south. So what's my displacement? 38 kilometers north. Okay, I went 100 kilometers north and then 62 south. So I ended up here. From my starting position, that's 100 minus 62, or 38 kilometers north of where I started. That's my total displacement for the whole trip. Okay, so I know my total displacement is 38 kilometers north. How long did that take me? 2.1 hours. The first part of this trip took 1.2 hours. The second part took 0.9 hours. So my total time is 2.1 hours. Now I can find my average velocity over the whole trip. It's going to be kind of small. Yeah, because I backtracked. Okay, that's always going to make your velocity smaller. Okay, so I backtracked, and I'm going to end up with 38 divided by 2.1. All right, so my average velocity is 18 kilometers per hour, what? North, right, because it's a vector quantity. Okay, last thing before the bell goes. What's my average speed over the whole trip? Remember that speed is distance over time. How far did I go? 162 kilometers, right? Distance doesn't care whether I went backwards and forwards, north and south. Just cares how far did I go. So that's 162 kilometers over 2.1 hours. Okay, 77.4 kilometers per hour. Do I need a direction on that? No. Okay, so same trip, two different points of view. We'll talk more about that tomorrow.